Previously, I took elements of Espen-Hoag's code, VBA code, for estimating the Cox Ross Rubinstein tree. It's a dynamic tree, and I also borrowed some insights from Quinn, who developed some C++ code to invoke MacDonald Schroeder. And the MacDonald Schroeder basically sets out pot call parity conditions that are useful for American pot options. Okay, so when we ran the estimation, I had some values from Lyson-Reimer, 1995, and I made the comparison, and the values are approximately the same, but not completely. So I went back and I ran additional estimations, but this time it was for, I'll just pause for a second. I'll take a look at a paper in the Journal of Finance 2000 by Bunch and Johnson. So again, it's a slightly earlier paper, but the reason why I'm taking a look at this paper is because they have actually some values worked out for American put options. So if I go to, I think it's table 1 or 2, just go back up, table 2. So I'll rotate, view, rotate clockwise. So we've these values for put options, so American put values, and then the parameters, so volatility 20%, we can have 150 or 10,000 steps in our tree, and each T here, T is not a year, it's actually a month, so 4 months is 0.333 of a year, it's a third of a year. Interest rate continuous is 488 or 5 discrete. Okay, stock price 40, and we start with exercise of 35, exercise of 40, exercise 45. So I'll bring up those values for a moment. So I have them here. So the last values. So here are the values, 10,000. Okay, so I'll just set everything up. So I have the Bunch and Johnson paper that has values for binomial tree, 10,000 step tree, and if we look at the values, 10,000 steps with 4 months, with volatility 20%, interest rate of 4.88 continuous, and stock price at least here initially at 40, exercise 35. So let's just see if I can verify those values here. So the stock price actually should be 35, is 40 given here, and then the stock price, the exercise price, should be 35. Okay, so let's just run, and volatility, we'll just check 20%. Now we have 10,000 steps, 10,000 steps. The value should be 0.2004, and that's what we have here. If it was 150 steps, 150 steps, 150, run again, then the value would be 0.1995, 0.1995. So this relationship that we've set out here, this code, C++ code, where we've dynamically structured the binomial, truncated the zeros, invoked MacDonald and Schroeder, and applied some of the insights from Quinn in terms of structuring the loops and defining num and so on. Once we run these estimations here, we seem to be getting results that are consistent. We can do one more check. Here the exercise is 40, not 35, otherwise the same. So I will just change this to 40. It's 150. When we run, the value that we should get for 150 is 15783. 15783. And then one bigger test then is for the 10,000 steps. So for a 10,000 step tree, again taking the same parameter coefficients, 10,000 step tree, the value should be 15798. We'll check 15798, and when we compare down here with the results 15798, we're getting the same result. So this code looks as if it's doing the job, even though when we compared with the Lyson-Reimer results for 15,000 step, there was slight differences. I think we probably have those are less apparent here, and the code looks highly accurate. So again, maybe one more test. I'll put in 45 just to be sure. Delete 5, 45 exercise, run, and the value I should obtain for exercise 45 for 10,000 step 3 would be 50883. 5.0883. Again, it's consistent results. Okay, so these results, this code then looks as if it's working properly. It works for both the using a call or a put, and for the European options it also works as well. So the code is functional. Now, one other additional thing we can do to speed up the code, it's been sitting there all the time, but I haven't really referenced it. One of the estimations that we perform here is when we generate the stock price for any given node, it's made up of two components, U and D. That's not surprising. That's how, I mean, at any point in the tree, basically when we go up we're multiplying by U, when we go down we're multiplying by D. So each of these nodes represents a kind of combination of U and D. Again, to see that, perhaps we might think of Hoag's representation here. So when we go up twice it's SU squared, when we go up and come back down it's SUD. When we go up and then back down, S squared, D squared. But if we note that U is equivalent to 1 divided by D, or D is equivalent to 1 divided by U, we would know that S is equal to S times U by D equal to S times U squared, D squared. And some of the estimations then in terms of U and D and those powers could actually be reduced slightly if we had a more efficient form, and that's a small improvement that we can introduce here. So this last results we did with a 10,000 step tree based on Johnson, Bunch and Johnson. If we make a couple of small changes here in terms of, instead of estimating S in terms of S power U, S by U to the power of I by D to the power of N minus I, we could have written this in a simpler form that involves only one power estimation. Okay, so again, to make the adjustment here, I'm going to remove the Z. Remember, Z no longer applies. I removed it when with the if statement, so Z is no longer here. In fact, I can take that Z as well, right? It's no longer in the estimation, in the declaration. I just need num and start, and Z is no longer there. And I got to remove, I should remove Z down here also, okay? Otherwise, how is this different to what went before? Well, if we go into the the spreadsheet for a moment and take a look at the tree, any S in the tree is made up of some combination of U and D. For instance, if I take S here, it's the current stock price. Let's say it's 100. If I go up and multiply then by D, so multiply by U, multiply by D, the fact that U is equal to 1 divided by D, or alternatively D is equal to 1 divided by U, when I multiply U by D, it reverts to 1. So the value here will be equivalent to the value here to the value here. Okay, so we have a lot of power terms that are gobbling up estimation and memory and so on. We can also observe that from the tree itself, that when we looked at this 15-step tree, notice that the center value every second column goes to 100, or goes back to the original stock price. Now that's a feature of Cox Ross Rubinstein trees, but we can see the maths behind that if we look at if we are aware that U, and we have it here, or D is equal to 1 divided by U. In other words, D multiplied by U has got to be equal to 1. Okay, now to make our algorithm a little bit more efficient, we take that into account and we re-express S not as being defined by 2 power functions but by 1. Okay, so by moving from this to this, and likewise down here moving from this to this, I'm eliminating a certain proportion of the estimations that's got to take place. So if I run this, we get a value of, now it should be faster first of all, so it's taking, in this instance, it's taking 3 seconds, and it's a value of 5.088, and that's consistent with the value we would have observed here, the 5.0883 for the 10,000 step tree, and it's taking just over 3 seconds. When I revert back to the former value, so if I use the more inefficient way of estimating the stock price in the Cox Ross Rubinstein tree, okay, I just changed 2 lines here. If we put / in, it just neutralizes the estimation. Right, so I'm going to do that here. Right, and let's just run that. Now currently it's taking 3 seconds with the efficient use of the power term. When we do it with the less efficient, we're going to get the same value, hopefully, in terms of the options price, but it's going to take longer. It's taking close to 6 seconds. So there's a fairly substantial burden of estimation taking place when we use this form as opposed to the more efficient form. We go from 3 seconds up to almost 6 seconds. Again, we recover the same value for the option, for the put option, but the time it takes is considerably higher when we use this approach as opposed to expressing S in terms of a single power function. Okay, one more thing in passing here. If we change the option to being European, okay, that should also considerably reduce the estimation time. Okay, so just to note that E and then inverted comma, and notice it takes 6 seconds. If we go with E, that should reduce considerably. It's down to half a second. And one of the reasons why it's falling so substantially here in terms of the estimation relates to the fact, again, when we look at our estimation for the European option, we're only discounting the time value. For the American option, we've got to take the difference. We've got to decide which is bigger, the time value of the option, the real time value, or the intrinsic value, and that's occurring at every node. And because it's occurring at every node, it's a fairly substantial burden to impose in terms of estimation.